心的澎湃。
Madrileña que paseas tu palmito, muy bien planchado, presumiendo con tu pie tan chiquitito, muy bien peinado, al mirarte así tan chula y costilera, a todos gustas una atrocidad. Por el salero que derrochas pinturera, cuando paseas por la calle de Alcalá. Monísima, 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 así te dicen cuando pasas por ahí. Monísima, 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 con tu blusita planchadita de organdí. Monísima, 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 te dicen todos al pasar, ole que sí, y te repiten con salero, monísima, por esas calles de Madrid. Son tus ojos, madrileña, dos luceros que hacen tilir, y tus mágicos andares pintureros son de postil, tu sonrisa ha conquistado al mundo entero por el salero que se esconde en ti. Y al ver tu garbo tan airoso y retrechero, así te dicen los castizos de Madrid.
Monísima, monísima, monísima,
así te dicen cuando pasas por ahí.
Monísima, monísima, monísima，
全新健达饼干，乐最棒，与您见面。
多陪陪自己，我要的生活就是这么单纯。保养也要。
填不满半排观众的电影，直到3场时突然亮起灯，字幕定格在某某出品和发行，我目送他们行色匆匆，像个字不量力的复读生，完不成金榜题名的使命，命不是财神到时都不得决定，那么任性。我吹过你吹过的晚风，那我们算不算相拥？可容梦初醒般的两手空空，心也空。我吹过你吹过的晚风，是否看过同样风景？想绕乱时差留在错位时空中，时空时空。十字路口闪烁不停的信号灯，有个人显然心事重重。3个字只能说给自己听，仰着头，不要让眼泪失控。哪里有可以风 回路转的宿命，我不想听。我吹过你吹过的晚风，那我们算不算相拥？可如梦初醒般的两手空空，心也空。我吹过你吹过的晚风，是否看过同样风景？想让人写下留在所谓时空中，时空，时空。我吹过你吹过的晚风，空气里弥漫着心痛，可我们最后在这所谓时空中升空。我吹过你吹过的晚风，空气里弥漫着心痛，可我们最后在这所谓时空中升空，升空。
添加自然更健康，
只想一口接一口。
西沙自然素材新上市，喝叶黄素。
Okay, so 90 degrees in radians, 90 degrees is pi over 2 radians. All we need to do is take our second sine wave and make it rotate 90 degrees ahead of the first one. Yeah, 90 degrees ahead. Okay, so 90 degrees in radians, 90 degrees is pi over 2 radians. Yeah, pi over 2. So then we just go to our second sine wave and change the thetas for theta plus pi over 2. Okay, now the second sine wave should spin ahead of the first one by pi over 2. And it does. Cool, a sine windmill. Simple but effective. And now we can add more sine waves. We can have 3 of them, like this. Same thing pretty much, except this time the second sine rotates ahead by pi over 3. And the third sine rotates ahead by 2 pi over 3. Okay? Okay. But you could add other numbers as well, if you want. But you know, I like these ones. Because this way everything is equally spaced out. Perfectly balanced, as all things should be. But of course you can have any number of sines you want. Here you go, 10 sine waves. First one spins by theta. Second one spins by theta plus pi over 10. Third one spins by theta plus 2 pi over 10. Fourth one spins by theta plus 3 pi over 10. And so on, etc, up to the last one which spins by theta plus 9 pi over 10. 10 equations needed for this one. 10 equations, blimey, that's a lot. Fortunately, we can condense these 10 equations to one single equation, like this. Alright, now, don't worry too much about the red stuff. The red stuff is just to generate the first original sine wave, just for the first initial one. But to generate the 9 other sine waves, that's what this black L is for. You see, Desmos has this inbuilt feature called a list. L is a list. Okay? It's a list because it has these square brackets on the sides, which normally doesn't mean anything. Normally, square brackets are the same as curved brackets. But for Desmos, they are not the same. For Desmos, square brackets indicate a list. And when Desmos sees a list, it will draw out a separate graph for each individual number in that particular list. Very handy, and much easier than copy-pasting 10 of these equations and then manually adjusting each theta by hand 36 times. I totally knew that before I made this. Moving on now. The next thing we're going to do is rotate our sine wave around a different point. Right, so up until now, we've only been rotating around the origin, 0, 0. But what if we wanted to rotate around the point 11, 5, for example? To do this, we are going to cheat. We're not going to rotate around 11, 5. What we're going to do is this. First, we translate the sine wave the exact opposite way, down to the point -11, -5. Okay, we just slide it down over here. And then we set it to rotate around the origin. Rotate around the origin, that's no problem, that's what we've been doing all this time. Okay, and then only now are we going to move it back up, back to where it was before. Like this. Alright, and now as you can see, now it rotates around the point 11, 5. Excellent, we're done. And for the general case, it is exactly the same process. First, we move our graph the opposite way, away from the red point. Okay, next, we set our graph to rotate around the origin. And finally, we move it back to where it was before. Okay, so as for the actual equations, here you go. To rotate around the point AB, x becomes x minus a cos theta minus y minus b sine theta plus a, and y becomes x minus a sine theta plus y minus b cos theta plus b. Looks complicated. But consider this. If we set a and b equal to 0, so in other words, if we set our graph to rotate around the point 0, 0, then indeed, yes, we do get back our original two formulas that we were using before. As expected. Anyway, windmill spinning around a different point. Yeah. Although, to be honest, it's not really a whole lot different. Except for this pointy ninja shuriken looking thing in the middle. It's alright, I guess. But we can do better. We can move the center around. Yeah, in fact, we can make it move automatically by letting the coordinates depend on theta. Ooh, now that's an idea. Let's try it. Let's try, I don't know, let's make it rotate around the point cos theta sine theta. What happens then? Ah, it goes in a circle. Oh, well, of course it does. Cos theta and sine theta, that's the parametric representation of a circle. Yeah, that explains it. As theta goes from 0 to 2 pi, the center travels along the circle. Makes sense. Now let's take a break from windmills for a moment and switch over to parametric graphs. Oh yeah, parametric graphs. I almost forgot about those. Oops. Anyway, yeah, we can still do the same thing. In fact, it's even easier in parametric. To rotate around a new point in parametric, all we have to do is add the point up. So the only real way to do that is anyway to use them. Okay, so if we reuse t, then it's going to start changing the shape. Okay, now this one is supposed to be a single spinning sine wave. A single sine wave. And if you tilt your head, maybe you can kind of see it in there. But it's being consumed by this giant field, what appears to be tan lines. Huh. This is supposed to be? Take a guess. Wrong. This isn't a sine wave. This is just a straight line. Yeah, it's a line. Y equals x. Line. Y equals x. The simplest graph of all. No, seriously, check this out. I can even graph the normal y equals x line on top, in red. And now you can sort of see it in there, spinning around. But as soon as I add in these two terms, sine of 5x and sine of 5y, wham! Our beautiful line just decomposes into this toxic foamy acid with bubbles. Place the x and spiral. How do we rotate the outside faster than the inside? Root of x. Root of x. What? But there are also, and it just keeps on wrapping. It never stops. If I let this go long enough, eventually it's going to turn the whole screen red. And then Desmos will start screaming in agony and probably eventually kill itself. And I will be left disappointed once again. But spirals work even better on parametric graphs. Well, I think they do anyway. In my opinion, they do. We can also invert the spiral, make the inside spin faster than the outside. To do that, instead of multiplying by the distance, we divide by the distance. And there are many, many more variations on the spiral that you can try. Just experiment with it. See what happens. I've been trying a few, and I've got some nice ones. Maybe I should make a compilation. Maybe I will. Anyway, there was still one last thing I wanted to show you, and I saved the best till last. We're gonna do a rotation in 3D. Yeah, that's right. Rotate in the third dimension. But not real 3D. Not real 3D. Okay, I'm not talking about adding in a z-axis or anything like that. Desmos doesn't even do a z-axis. Nah. We'll still be in our 2D plane, but we can project a 3D rotation onto the 2D plane. A projection. 3D onto 2D. Wow. Now this is some really advanced stuff. Vector spaces and linear transformations, matrices and quaternions, homotopy groups, Lie groups, differential algebraic topology, Motezuki interuniversal Tesh-Muller theory, and the generalized continuum hypothesis. No, I'm just kidding. I'm just messing with you. Don't worry, it'll be fine. We'll be fine. But it doesn't matter anyway, because we've run out of time again. Ugh. Oh well. Part 3. I will see you there. Make sure you subscribe. Please. Any graph by any angle. Alright, I don't want to run out of time again. I want to finish up this time. So let's just jump into it. 3D linear algebra, in other words, linear transformations and matrices. Yay! Here's the thing, either you've studied linear algebra before, 15, so if you want to learn about this stuff properly, the proper way, there's like a billion.
亚英耍任性，吃美食不尽兴，你是要亚洲式双重专户。
Part 3, how to rotate any graph by any angle. Alright, I don't want to run out of time again, I want to finish up this time, so let's just jump into it. 3D rotations, here we go. I'm going to show you 2 ways to do a rotation in 3D. There's the easy way, and there's the beast way. We are going to do both, but first we'll begin with the easy way, using the power of linear algebra. Linear algebra, in other words, linear transformations and matrices. Yay! Here's the thing, either you've studied linear algebra before, and you already know exactly what a matrix is, and what a linear transformation is, and me explaining it to you is going to be as interesting as an engineering lecture. Or you haven't learnt linear algebra yet, in which case it will take me like 15 minutes to explain. Unacceptable. Nope, we have no time for that, so if you want to learn about this stuff properly, the proper way, there's like a billion other videos out there. 3 Blue 1 Brown has probably done a whole series on linear algebra, probably with his absolute perfect animations, specially made in his custom-built Python library. First of all, what is a linear transformation? Why don't I just show you? A linear transformation allows us to do things like stretch out the x-axis and the y-axis. But more than that, we can also change their directions. We can make the x-axis go up at an angle. Yeah, and we can also move the y-axis around too. We can flip the plane all the way around if we want. Rotate it, skew it, stretch it, squish it, etc. All of these are linear transformations of the plane. Okay, now technically there's no 3D in this at all. Technically there's no 3D, but it kind of looks like there is. Kind of looks like we're angling up the normal 2D plane and rotating it around in the 3rd dimension. Yeah. Alright, anyway, let's go back to our good old sine wave, y equals sine x. Of course, we know how to rotate this around the origin. Change the x's, change the y's, yeah. But now consider this. What would happen if we did a linear transformation on the plane while the sine wave is still spinning? There you go, a 3D rotation, naturally. Okay, that's great. How does this work mathematically exactly? Well, if you've learnt linear algebra before, you'll know the way we encode a linear transformation mathematically is using a matrix. Specifically the matrix ABCD. And the official rule goes like this. The matrix ABCD times the point xy equals the new point ax plus cy, bx plus dy. But the truth is, this rule, it doesn't really matter. And the matrix itself doesn't really matter either. All that matters is we start at the point xy, and the linear transformation tells us to go to the new point ax plus cy, bx plus dy. Okay? Or to put it another way, the x-coordinate turns into ax plus cy, and the y-coordinate turns into bx plus dy. That's what the linear transformation does. So, let's come back to our sine wave. And we just do the same thing. Change the x's into ax plus cy, and change the y's into bx plus dy. Alright, now for some examples. First of all, note that if we let a equal 1, b and c equal 0, and d equal 1, then we get back our normal flat spinning sine wave. Alright, so what about if we increased d to 3? Looks like it's facing up more vertically. Alright, what if we increase a instead? Ah yeah, now it faces out horizontally. Okay, and if we start changing b and c, that's how we get it to face a diagonal direction. In theory, you can do any direction, but the tricky part is figuring out how to choose A, B, C, and D. Meh, whatever. If you know linear algebra, you can do it by calculating the inverse matrix and mapping the standard basis vectors, but that's annoying. And besides, if you stare real closely, you might notice that something ain't right. This is actually not a true, proper 3D rotation. In proper 3D, things appear bigger when they are closer to you, and they appear smaller when further away. But sadly, linear transformations don't do that. Linear transformations keep everything the same size. So, you know, it's kind of a cheat. And you know what that means. Finally, the moment you've been waiting for. But in order to do a perspective projection, we're going to have to switch to 3D geometry. Yeah, we're gonna need a z-axis. But Red, you said we wouldn't need a z-axis. Yes, I did. I lied. Nah, here's the thing. There's 2 steps. Step 1, we convert our graph into 3D and rotate it properly in 3D space. Okay? That's what we need the z-axis for. And then, step 2, we project the 3D space onto our 2D plane. That's the projection, and that's when we'll get rid of the z-axis. Yes, we'll get rid of it in the end. Don't worry, but we need it to begin with. Trust me. Actually, no, don't trust me. You know what, screw it. Let's just do the projection part first. Why not? So we're in 3D space now. That means our points are no longer just 2 coordinates, they have 3 coordinates, x, y, z. But we don't want them to have a z coordinate, so we have to find a way to send any 3D point to the usual xy plane. Okay, so one way we could do this is by sending xyz to the point xy0. In other words, basically we just drop the z coordinate. We could do that, and in fact, actually we already did that, back when we did the linear transformation. That's what the linear transformation was doing. But it's not the only way to do it. There is a better way. Imagine you are standing on the z-axis. You're on the z-axis and staring directly at the xy plane. Okay, what we can do is draw a straight line from your eyes to the point P. This line goes through P, and somewhere along it hits the xy plane at some new point. Okay, now we're going to define this new point to be our projection of P. Okay, so you can imagine this line is like a ray of light that's coming from the point P, and it's hitting your eyes. That's how you see things. Literally, that's how you see. But if you were to draw what you see in real life onto a 2D screen, like the xy plane, then of course you would draw P at its projection. And that's the idea. Okay, so how do we do this mathematically? First, we need to decide where we are exactly on the z-axis. I'm going to choose the point 0, 0, 30. But you could choose any other point you want. It doesn't matter. Although, I do recommend not choosing one that's too close to the origin, because then you might not be able to see much. Anyway, I'm not going to go through the actual maths, but basically we just connect 0, 0, 30 to the point P to get the line that goes through both of them, and then we can find the point on that line where the z coordinate equals 0. That gives us the projection point, and it turns out to be 30 divided by 30 minus z times xy0. 30 divided by 30 minus z times xy0. Projection complete. Now all that's left to do is drop the 0. Yep, we just get rid of it. 30 over 30 minus z times xy. And we are back in 2 dimensions again. Back in 2D. Nice, that's it. To project our 3D point XYZ onto the XY plane, we just convert it to 30 over 30 minus c times x. Big box. Remember this. Do not forget. This is very important, and we will need this later. Because that was step 2. Now we gotta go back and do step 1, the actual rotation. First things first, we gotta choose our graph that we want to rotate. And that's actually not so easy to do in 3D. For example, in 2 dimensions, we can just write y equals sine x. And that gives us a thing squared equals contains only lines. Now we could write something like y equals sine x equals z. And that does work for simple graphs. But if I write something more complicated, like y squared equals sine of xz equals x plus z, that's impossible. I have no idea what this even looks like. And computers don't either. Probably no one knows. So long story short, for 3D, we're just gonna abandon Cartesian equations. No more Cartesian, only parametric. And parametric is much better. X equals f of t, y equals g of t, and z equals h of t. We're pretty much guaranteed on those. So long story short, for 3D, we're just gonna abandon Cartesian equations. No more Cartesian, only parametric. And parametric is much better. X equals
Cartesian.
And parametric is much better. X equals f of t, y equals g of t, and z equals h of t. We're pretty much guaranteed to get a line with this. For example, we can try x equals t, y equals sine t, and z equals t. This is the graph of a diagonal sine wave. If we change z equals t to z equals 0, then we get a flat sine wave. What if we swap x and y around? Then we get a... If we change z equals t to z equals 0, then we get a flat sine wave. What if we swap x and y around? Now it becomes a vertical sine wave. Now it becomes a vertical sine wave. My favorite one is a spring. X equals cos t, y equals t, and z equals sine t. And there's more you can try, obviously, but sometimes they can get a bit hard to wrap your head around. That's why I like the spring. It's very intuitive, but not trivial. But it doesn't matter anyway, because in general, every parametric graph has the form x equals f of t, y equals g of t, and z equals h of t. Yep, we're just going to go straight for the general case, like men. We can try some examples at the end. This is our graph. Alright, now we want to rotate it. How do we do that? With this! Ta-da! I got this off Wikipedia. It's called Rodriguez's rotation formula, named after the legendary Olinde Rodriguez. Never heard. Anyway, this is the equation we're going to use. Except there's one little problem. Okay, a few problems actually. For starters, this formula is designed to work for vectors. Basically, you give it a vector v, and Rodriguez's formula spits out v theta, which is your vector v rotated around by theta. So we're going to have to find a way to convert these vectors into 3D parametric graphs somehow. Okay, that's not too hard. But more importantly, what is k? K is another vector which describes the axis of rotation. So okay, yeah, you've got your vector v, and you want to rotate v, but you gotta tell me what axis you want to rotate it around. Do you want to rotate it around the x-axis? Or rotate it around the y-axis? Or the z-axis? Or a diagonal axis? Okay, we need to decide that. That's what k is for. For example, if you want to rotate around the x-axis, then you would choose k to be the vector 1, 0, 0. Or to rotate around the y-axis, let k equal 0, 1, 0. For the z-axis, k then use and on the g of t equal 1, b equals 0, c equals 0, then crunch through all the numbers and oh, what do you know? It actually worked. Can we change the rotation axis? Let's see. Let's try b equals 2. Don't forget to normalize. And nice. It doesn't have to be a 3D graph though. Just set h of t equal to 0, and we can get back our original 2D graphs from before. For example, here is our good old sine wave, spinning around the y-axis. Can we make a windmill again? Yes, we can! Oh. What is this? Abomination! It looks horrible! Oh yeah, because we're looking at it from the side. Alright, let's just tilt it forward a little bit. Yeah. Wait a minute. Oh no. Now the sine waves are all wrong. They're not flat. They should be flat, like this. How do we fix this? It's actually not totally trivial. But what we can do is use our rotation formula twice. So we begin with our regular sine wave. Nothing special yet. But before we make a windmill, first we use our formula to rotate the sine wave around the x-axis. Yes, that's right. Not the y-axis, the x-axis. So now it's facing down, slightly diagonal. And now we use our rotation formula again to spin it around on an angle like before. And then finally, we can add in the other sine waves to make a proper windmill. Anyway, this is the end now. I am done. I am so burnt out. But I did have some more things I wanted to try. Like I was thinking about a 3D spiral vortex. Not sure what that even means, to be honest. but I don't know, maybe it could be something. Or how about a 4D projection? Yeah, a 4-dimensional hypergraph. Now that would be cool. And it's definitely doable, I'm pretty sure. But how? That I do not know. I know nothing about 4 dimensions. What does a 4D spring even look like? Imagine if I could just type in some numbers and Desmos would show me.
的机会，二人一起在学院季里闲逛。逛的时候，他还不忘夸一波粉毛的衣服。对此，粉毛的反应是这样的：毫不脸红，毫不害羞，男主还需再接再厉啊！粉毛没有因他的话产生任何动摇，结果没过多久就被男装红毛夺了心。红毛作为前一任男装选美的冠军，看中学院里的偶像。果然，这女人要是帅起来，就没了平时绿毛的药能有，莫不是？男主这还写着本性暴露几个大，男主便的斗志，主全部归罪于绿毛的钻进去们见此相遇后还提起性，孩子们后还把公白机车拖延，男主将这下是发礼物。就在这时，红毛的弟弟提出，驯鹿的工作并不是派发礼物，而是驮着圣诞老人当坐骑。看不出你年纪不大，想法倒还挺多，未来肯定能成为一个合格的绅士。男主推辞不掉，只能让白毛纵了上来，结果只是一下他就感觉到了不对，这个触感，这个体温，白毛貌似没有称胖子，这下坐骑变成了真坐骑。男主驮着白毛瞬间消失在了门口。圣诞派对结束后，红毛和男主来到院子里聊天，男主将自己做的小奖牌送给了红毛，说是驯鹿送给圣诞老人的礼物。被他这么一搞，红毛脸红心跳，二话不说就打算献上香吻，当做圣诞压根就后就会想房间可能在其实由于白毛的门此空间乱得像个垃圾堆，但对比白毛的房间标准绿毛便到这边用了全他的男主亲着他，这让白毛感到是毛已经醉得差不多了。男主顾不上的挡在后话说半实在，男主也打这把众人喜人纷纷经过他男早男这样下好的个只能干。
白天则会周末不专辑，雪花也未曾想过自己，规则竟是脚下的泥地，是从了最自由发挥，有什么坏事？
控制力也很好。
我们互不相欠，何必隔着屏幕消下你的偏见？别听我说，听我说，听我说，别听我说，听我说，听我说，我闭上嘴巴，不做挣扎，反正你都听不见。听我说，听我说，听我说。
YouTube Music 有多种情境的播放清单，像是你在跟深蹲奋斗的时候，试试 YouTube Music Premium。
而你正在拥我入怀中，一字一句誓言多慎重，你眼中有柔情千种，如脉脉春风，冰雪也消融。那年长街春意正浓，策马独游，烟雨如梦。檐下多雨忘记一说，深邃眼瞳，宛如华山夹着细雪的微风。雨丝微凉，风吹过岸上朦胧，一时心头悸动，似你温柔剑锋，过处翩若惊鸿。是否情字写来透空洞，一笔一画斟酌着风颂，甘愿卑微换个笑容，或沦为平庸。而你正在拥我入怀中，一字一句誓言多慎重，你眼中有柔情千种，如脉脉春风，冰雪也消融。后来谁家谁眼重逢，佳人在侧，烛影摇红。灯火缱绻映照一说，如花颜容，宛如豆蔻枝头温柔的旧梦。对面不是恍然间思绪翻涌，望你白衣如旧，神色几分冰冻，谁知我心惶恐。也许我应该沉醉装疯，借你怀抱留一抹春红，再将旧时情歌慢诵，任旁人惊动。可我只能假笑般从容，侧耳听那些情深意重，不去看你熟悉脸孔，只默默饮酒，多无动于衷。山门外，雪拂过白衣，又在指尖消融。抚长剑，试问江湖若大概何去何从？几声至此，像个笑话一样，自己都嘲讽。一厢情愿，有始无终。若你早与他人两心同，何苦惹我错付了情衷？难道看我失魂落魄，你竟然心动？锁进今年漂浮红尘中，这颗心已是千疮百孔。怎惧你一波情为人，添一道裂缝，又不会痛。不如将往事埋在风中，以长剑为背，以霜雪为重。此生若是错再相逢，求一个善终。孤身打马难堪九桥冰火，恰逢山雨来时雾蒙蒙。想起那年伞下轻拥，就像躺在绞索之上做了一场梦。梦醒后跌落，粉身碎骨，无影亦无踪。
藏一颗死心，苦苦的追寻，茫茫然失去，可爱的可恨的多可惜。梦中的梦中，梦中人的梦中，梦不到被吹散，往事如风。空空的天空容不下笑容，伤神的伤人的太伤心。何必想，何必问，何处是我家？爱也罢，恨也罢，算了吧。问天涯，望断了天涯，赢得了天下，输了他。挥别的种种，回不去的种种，回不了被淹没一往情深。人已无可忍，恨不得别人，害人的迷人的痴情人。也挣扎也牵挂也不是办法，走也罢，留也罢，错了吗？今天涯，明天又天涯，狠狠一巴掌，忘了吧。牵挂也不是办法，走也罢，留也罢，错了吗？今天涯，望断了天涯，狠狠一巴掌，忘了吧。梦中的梦中，梦中人的梦中，梦不到被吹散，往事如风。空空的天空容不下笑容，伤神的伤人的太伤心。问天又问地，忍不住的流星，谈不上被恨藏一颗死心。苦苦的追寻，茫茫然失去，可爱的可恨的多可惜。梦中的梦中，梦中人的梦中，梦不到被吹散，往事如风。空的天空容不下笑容，伤神的伤人的太伤心。啦啦啦啦啦啦啦啦啦啦，啦啦啦啦啦啦啦啦啦，啦啦啦啦啦狠一巴掌，忘了吧。
关闭荧幕也能享受音乐，不受干扰。免费试用 YouTube Premium。
想要零广告、下载音乐并离线播放及背景播放吗？试试 YouTube Music Premium。
也许争不过天与地，也许低下头会哭泣，也许艳阳雪要飞进心里，会有孤立将出不去，一生与冷漠做邻居，悲壮时光已夺走你什么？在人间有谁活着不像是一场竞技？我不哭，我已经没有怎也能放弃。当某天那些梦爱亏欠在人海里边难过，让它去，这首歌就当是赠礼，挂在脸孔上是面具， 间里，你到底为了什么而不去？人心有多时不坚定，灵魂在逃亡无处去，现实像成了我是只蚂蚁。
Upgrade complete.
I am prepared. It has begun. For my brothers.
Job's done. Job's done.
Enlighten me. That's a given. For my brothers. No one
Job's
should be
done.
wiser.
Job's done. Job's done. Job's done. Job's done. Job's done.
Out with it. For my brothers.
Job's done.
Thy bidding. Out with it.
Say the word.
Thy bidding. Out with it.
Research complete.
I am prepared.
Upgrade complete. Upgrade complete.
I am prepared.
Someone call for the doctor.
I stand ready.
Thy bidding. Out with it.
Upgrade complete.
Enlighten me.
I stand ready. I stand ready.
I am prepared. bidding.
Yes, my liege.
Enlighten me.
Research
complete.
Orders?
I am prepared. Enlighten me. Has begun.
Job's done.
Thy bidding. Enlighten me. Thy bidding.
Build more farms. Job's done. Build more farms.
Don't be afraid.
I am prepared.
Upgrade complete.
Has begun.
Job's done.
No one shall be the wiser.
Research complete. Job's done.
Enlighten me. Out with it.
Someone open it up.
Brothers.
Job's done.
Hey, sailor.
Thy bidding.
Upgrade complete.
Has begun. Enlighten me. Out with it.
Job's done.
Enlighten me. me. That's a given. I am prepared. It has been
Job's done. Job's done.
Out with it.
Upgrade complete.
I am prepared.
Upgrade complete.
No one shall be the wiser.
Are there enemies above? Job's done.
Out with it. I bid you. Prepared. Thy bidding.
Upgrade complete.
I am prepared.
Upgrade complete. Job's done.
Thy bidding.
Upgrade
Who do you
complete.
want to kill? Out with it. Do you want axe? Thy bidding. Thy bidding. brothers.
Job's done.
Enlighten me. I am prepared.
Upgrade complete.
What do you need? Enlighten me.
Say the word.
Out with it.
Job's done.
Orders.
What do you need? Job's done. Say the word. Yes, my liege. Orders.
I bid it.
Feel free.
Enlighten me. Out with it. Enlighten me. That's a given. No one shall rise.
Job's done.
My bidding.
Upgrade complete. Upgrade complete.
That's a given.
Job's done.
Out with it. For my brothers.
Upgrade complete. Job's done.
My bidding.
Upgrade complete.
It has begun. I am prepared.
Job's done.
For my brothers. No one shall be wiser.
Job's done. Job's done.
Has
Job's
begun.
done. Job's done. Job's done. Job's done. Job's done. Job's done.
Enlighten me. I am prepared.
Research gold is required.
Out with it. I bid. Out with it.
Ready to work.
Out with it. Enlighten me.
I cannot summon
My brothers.
Job's done.
I I am prepared. Thy bidding. Washiwa. I am prepared. It has begun.
Upgrade
no one shall be
complete.
the wiser. Thy bidding. For my brothers. That's a given. I am
Job's
prepared.
done. Job's done.
Enlighten me. Out with it. No one shall be the wiser.
Research complete.
For my brothers, no one shall be the wiser. That's a given. Enlighten me.
Job's done.
I am prepared. Out with it. I am prepared. Out with it. Thy bidding. No one shall be
Upgrade complete.
It has begun. For my brothers.
Job's done. Job's done.
Out with it.
Upgrade complete.
Enlighten me. I am prepared.
Upgrade complete. Upgrade complete.
It has begun. For my brothers. Out with it.
Job's done.
I am prepared. Prepared. Enlighten me.
Upgrade complete.
My bidding.
Job's done.
My song is yours.
Enlighten me. My bidding.
Waiting on you.
Out with it. Thy bidding. Enlighten me.
Upgrade complete.
It has begun. For my brothers. That's a given.
Job's done.
One shall be the wiser.
Job's done. Job's
Thy
done.
bidding.
Job's done. Upgrade complete. Upgrade complete. Upgrade complete.
Enlighten me.
Job's done.
Thy bidding.
Upgrade complete.
Someone call for the doctor?
Beelzebub!
Out with it. It has begun. For my brothers. It has
Job's
begun.
done. Job's done.
I pledge my loyalty.
Enlighten me. I am prepared. No one should realize. For my brothers.
Job's done.
No one
Job's
should
done.
realize.
Job's done. Job's done. Job's done.
I bid you.
Upgrade
For
complete.
my brothers. It has begun.
Job's done. Job's done. Job's done.
Out with it.
Upgrade
No one should
complete.
realize.
Job's done.
I bid you.
Upgrade
Enlighten
complete.
me. I am prepared.
Upgrade complete.
Get on with it. I bid you.
Upgrade complete.
Out with it. I bid you.
Upgrade complete.
Enlighten. For my brothers. That's a given. No one shall be the wiser.
Job's done. Job's done. Job's done. Job's done. Job's done. Job's
My
done.
bidding. Enlighten me.
Waiting on you.
Upgrade complete. Upgrade complete.
It has
Upgrade complete.
For my brothers. It has begun. For my brothers.
Job's done.
Out with it. It has begun.
Upgrade complete.
No one shall be the wiser. That's
Job's done. Job's done. Job's done. Job's done.
No one shall be the wiser.
Job's done. Job's done.
Say the word.
I am prepared.
Upgrade
For my
complete.
brothers.
Upgrade
That's a
complete.
given.
Upgrade
For
complete.
my brothers.
Job's done.
My bidding. Prepared. Bidding.
Our time is now.
Out with it. No one shall be the wiser. That's a given.
Job's done. Job's done. Job's done. Job's done. Job's done. Upgrade complete.
Enlighten me.
Build more farms. Build more farms. Build more farms. Build more farms. Upgrade complete.
Our time is now.
Upgrade complete.
Our
Upgrade
time is
complete.
your move.
I am prepared.
Do you want axe?
Upgrade complete.
My song is yours.
Who'd you want to kill?
I am prepared. That's a given. For my brothers.
Job's done, job's done. Job's done. Job's done, job's done, job's done.
That's a given.
Waiting on you.
Job's done. Upgrade
complete.
No one shall be the wiser. For my brothers.
Job's done. Job's done, job's done, job's done.
Upgrade complete.
I am prepared. No one shall be the wiser.
Upgrade complete.
Job's done.
Out with it.
I wish only to
I
serve.
bid you.
Upgrade complete.
For my brothers. No one shall be the wiser.
Job's done. Job's done.
Out with it.
Upgrade complete.
For my brothers.
Upgrade complete.
I bid you.
Job's done.
Out with it.
Upgrade complete.
I bid you.
Upgrade complete.
No one shall be the wiser.
Job's done.
Upgrade complete.
I pledge my loyalty.
Research.
该怎么说？心里面在想什么？闷骚的性格我也很讨厌这结果。你看我的眼神，像是在把委屈诉说。Hey baby， 这都怪我，真的舍不得你难过。
不在乎别人怎么看，像我这种主动的女孩，越过暧昧需要多勇敢，难免会左右为难。你知道我对你不仅仅是喜欢，你眼中却没有我想要的答案，这样逻辑若力让我很抓狂。No， 看着吗？
你知道我对你不仅仅是喜欢，想要和你去很远的地方，看阳光在路上洒下了浪漫，当作我对你表白吧。
感情，最后我无意的看清，强悍的
不知道该怎么说，心里面在想什么？闷骚的性格我也很讨厌这结果。现在我也为你去改，从单绝变成行动派。原来我这无形的伤害，Because I love you so much。
不要想你只是
你说爱本就是梦境，跟你借的幸福，我只能还你。想留不能留才最寂寞，别说完温柔只剩离歌，心碎间一秒，用力的相拥着沉默，有些歌送你心酸离歌。
想要和你去很远的地方，看阳光在路上洒下了浪漫，当作我对你表白吧。
知道我对你不仅仅是喜欢，你眼中却没有我想要的答案。No， 看着吗？
你知道我对你不仅仅是喜欢，
是种
想要和
任
你去
性，
很远的
该
地方，
太
看阳光在
多考虑，
路上洒下了浪漫，当作我
爱
对你
没有
表白吧。
聪不聪明，只有愿不愿意。
希望这是你心的。
你爱是选择回去，它刺痛你的心，但你不肯觉醒。
是 YouTube 制作的音乐应用程式。
你说爱本就是梦境，可你借的幸福，我只能还你。想留不能留才最寂寞，被说完温柔只剩离歌，心碎间 could tear us apart till the day you broke my heart。And you know what， 我亲爱的你大事不妙。Mirror, mirror on the wall, I don't need you anymore. I'm the spoilers of the bar. CDLLLXXVIII, my girl, you can't understand.
做
多料理，不受广告干扰，免费试用 YouTube Premium。关键要人体实证，水亮度提升。
Complex numbers have a bit of a mystique around them, don't they? Before learning about them, and even afterward, I think many people view them as this mysterious or advanced number system, mainly useful for solving similarly mysterious or advanced problems. After all, they're built using a strange so-called imaginary number called I, defined as the seemingly nonsensical square root of -1. And though people may fear them, they usually respect them for being these powerful tools that they could never properly understand or wield on their own. But that's just not true. Once you get used to them, complex numbers are actually one of the most elegant and, ironically, simple to use tools in your mathematical arsenal. And personally, I think it's a big shame that more people aren't shown their utility as an ordinary mathematical tool, and instead the focus seems to be on how mysterious and magical they apparently are. So in this video, I'd like to share the less mysterious or magical side of complex numbers, and show how I've often found them handy to solve some tricky, but still very ordinary, problems. To show that their use is not limited to just quantum mechanics, advanced differential equations, or something like that. That they can be very friendly tools that everyone should feel comfortable having in their mathematical toolkit, and how not knowing them can be a real handicap sometimes. Note that for this video, I will be assuming you know a little bit of basic calculus, mainly derivatives, but even if you don't, I'll be trying to present things from an angle that you can hopefully still follow and get a lot out of. I'll write things from an angle that you can hopefully still follow and get a lot out of. Alright then, let's get started. To start things off, let's review the basics of what complex numbers are and how they operate on each other. The basic building block of complex numbers is I, the square root of -1, an imaginary number, if you will, that has the special property that multiplying it by itself yields -1. It can be added to itself and multiplied by real numbers to get other imaginary numbers that are multiples of I, like 2i, 3i, -4i, or 6.28i. You get a so-called complex number by adding a real number and an imaginary number together, like 3 plus 4i or -1 plus 1.5i. These expressions are treated as atoms. They don't simplify any further, and you can visualize them as points in the complex plane, where the x-axis tracks the real part, and the y-axis tracks the imaginary part. From this perspective, we can define the absolute value of a complex number as how far away it is from 0, or the origin, within this grid system, which you can compute by using the Pythagorean theorem on both the real and imaginary parts. So for example, the absolute value of 3 plus 4i works out to be 5. Now, two complex numbers can be added together by adding their corresponding real and imaginary parts, similar to how adding two vectors works. But unlike vectors, you can also multiply complex numbers together to get another complex number. And it works how you might expect by following the distributive rule and remembering that I squared is actually -1 and simplifying from there. And remembering that I squared is actually -1 and simplifying from there. It might not be clear yet what complex number multiplication means geometrically, just looking at these 3 points, but it actually has a very straightforward interpretation, which will be key to their geometric usefulness. To understand it, take a complex number z, like 3 plus 4i here, and multiply it by a complex number w that sits on the unit circle. That is, a complex number whose absolute value is 1. You might notice that the product zw looks like a rotated version of z, and indeed it is. In fact, multiplying z by w rotates it around the origin by the angle w makes with the positive real axis, in this case an angle of 70 degrees. So multiplying a complex number by a complex number of absolute value 1 just rotates it. This makes complex numbers a useful tool for representing and computing two-dimensional rotations. For example, if you want to calculate the coordinates of where a point like 2, 3 ends up after being rotated, say 30 degrees counterclockwise around the origin, all you need to do is find the complex number on the unit circle that is 30 degrees counterclockwise off the positive real axis and multiply it by 2 plus 3i. If you know a little trigonometry, this isn't too hard to do. The xy coordinates of the point 30 degrees along the unit circle are given by the cosine and sine, respectively, of 30 degrees, which work out to be about 0.87 and 0.5. So our point w can be expressed as the complex number 0.87 plus 0.5i. Multiplying it by our original point 2, 3, expressed as the complex number 2 plus 3i, we get that it's about 0.2 plus 3.6i. And looking at the picture, it matches up with where 2, 3 ends up after being rotated 30 degrees. Now, since this is such a common thing to do with complex numbers, it would be handy to have a shorthand way to refer to the complex number on the unit circle that is a given angle theta away from the real axis. And luckily, we have one. If you raise e to the power of the imaginary number theta I, where theta is measured in radians, the complex number you get is cosine of theta plus I sine of theta, which are the precise coordinates of the point we want. This relationship is called Euler's formula. Now, I won't go into why Euler's formula is true in this video. Anyway, there are already many other resources that can explain it probably better than me. But for now, you can think of e to the theta I as a funky way to represent the complex number on the unit circle that is theta radians counterclockwise from the positive real axis. But as you'll see later, there's actually a very good reason for thinking of it this way, besides just shorthand. Now, as for multiplying by complex numbers that are not on the unit circle, it's the same basic idea. You rotate by the angle it makes with the positive real axis, but then you also scale the rotated point away from the origin by the absolute value of the number that multiplied it. For example, multiplying the complex number 3 plus I by -1 plus 2i produces -5 plus 5i, which is what you get by rotating 3 plus I by the angle -1 plus 2i makes with the positive real axis, and then scaling it up by the absolute value of -1 plus 2i, which is square root of 5 in this case. This is the key geometric interpretation of complex number multiplication. Multiplying by a complex number rotates and scales a point, as opposed to real number multiplication, which only scales. So complex multiplication provides a very natural way to describe two-dimensional rotations. And because of this, complex numbers are often super useful for problems involving rotational motion or rotational symmetry. Complex numbers are the language of 2D rotation.
谁想伪装自己？谁能看见我眼里无助而流下的泪滴？别再说我变了，谁都别再提起，别再说了，我喜欢现在的自己。许多事已经看淡，偶尔还会期待。我是真的
Job's done. Job's done.
Show me the wiser.
Research complete.
Job's done.
What is your will?
像个影子，默默陪伴着
It has begun. No one should
Job's
be the wiser.
done. Job's done. Job's done.
是水中的脸庞，像那太阳，温暖着我。你说要带我走天涯，为了梦想，去远方流浪。远方的天空，是否会不同？ 天长地久。想要对你说的还是什么？想要对你说会永远陪你。我想要对你说，想要对你说我有多爱你，想要对你说我有多想你，想要对你说的一字一句都刻在我心里。想要对你说的天长地久，想要对你说的还是什么？想要对你说会永远陪你，我想要对你说。
I am prepared. My bidding. That's a given. My brothers, I am prepared.
Job done.
Out yours.
Upgrade complete.
I am prepared. Out with it.
Build more farms. Build more farms. Build more farms. Upgrade complete. Job's done.
I bid you.
Build more farms.
No one should be wiser. My brothers.
Job's done. Upgrade complete.
I bid you. I am prepared. Thy bidding. Out with it. I am prepared. Out with it.
Upgrade complete. Job's done.
Out with it.
Upgrade complete.
It has begun.
Job's done.
I bid you. I am prepared. Out with it.
Upgrade complete.
No one should be wiser. It has begun.
Job's done. Job's done.
McDonald's back.
I bid you.
you require aid, human?
YouTube Music Premium 让你完整掌控你的音乐聆听体验，享受零广告，下载音乐并离线播放及背景播放。试试 YouTube Music Premium。
那年长街追承诺，策马都有烟雨如梦，檐下多雨忘记一说，深邃烟土宛若华山夹着细雪的微风，雨丝微凉，风吹过岸上朦胧，一时心头悸动，似你温柔剑锋，我出片若惊鸿。一笔一画转调成风风，但愿这里花山中，我为平庸。那一生残拥我怀中，一字一句是我深重，一眼中有梦想中，如我冰雪眼笑容。恍然间思绪翻涌，望你背影如旧，神色几分冰冻，谁知我心惶恐。也许我应该沉醉装疯，借你怀抱留一抹春红，再将旧时情歌慢诵，任旁人惊动。可我只能假笑般从容，侧耳听那些情深意重，不去看你熟悉脸孔，只默默饮酒，多无动于衷。山门外，雪拂过白衣，又在指尖消融。赴长街，试问江湖若大概何去何从？几声至此，像个笑话一样，自己都嘲讽。一厢情愿，有始无终。再举你一波情天一道热风，又不回头，不如
上被冷藏一颗死心，苦苦的追寻，茫茫然失去，可爱的可恨的多可惜。梦中的梦中，梦中人的梦中，梦不到被吹散，往事如风。空空的天空，容不下笑容，伤神的伤人的太伤心。何必想，何必问，何处是我家？爱也罢，恨也罢，算了吧。问天涯，望断了天涯，赢得了天下，输了他。回跌的种种，回不去的种种，回不了被淹没一往情深。人已无可忍，恨不得别人，害人的迷人的是情人。也挣扎，也牵挂，也不是办法，走也罢，留也罢，错了吗？今天涯，明天又天涯。
To see what I mean, consider this example. Let's say you have a point moving in 2D space around the origin in some kind of irregular way. Maybe it represents the motion of a charged particle in an electric field or something. Let's say the point's xy position at any time t is given by two functions, x of t and y of t, and we want to compute its angular velocity around the origin at any time t. That is, how fast the angle it makes with the positive x-axis is changing at any given moment, or the time derivative of the point's angle function. To compute this, we would presumably need to first calculate the point's angle function at any time t from its two xy position functions, so we can then take its derivative. There's some subtlety required to do this right, which I'll skip over, but it can be done. It's possible to define a function that takes the xy coordinates of a point and outputs an angle in the range 0 to 360 degrees, or 2 pi radians, representing the counterclockwise angle the point makes with the positive x-axis. Throw in x of t and y of t into this function, and we have our angle function, theta of t. But here we run into a subtle problem. This angle function is not continuous. If x is positive and y moves from being negative to being positive, the computed angle will abruptly switch from being around 360 degrees to being around 0 degrees. So if you're trying to measure the angular velocity by, say, measuring how much the angle changes in a short period of time, but the point happens to be very close to the positive x-axis, you can wind up comparing angles from two sides of the seam and accidentally calculate a wildly wrong angle difference. What we'd really like is for the angle function to not wrap around to 0 if we started from around 360 degrees. But unfortunately, there's no way to easily do this. Angles are cyclic by their very nature. 405 degrees is the same as 45 degrees, and there's no real way to tell the difference between them without remembering the entire prior history of the point's motion, which would be a hassle. So, entire prior history of the point's motion, which would be a hassle. So are we stuck then? Is there no easy way to calculate a local change in angle just using local information about the point's motion? Well, turns out there is a way. The trick is to calculate the derivative of the angle function indirectly without having to know its full angle function in advance. And complex numbers provide a sneaky way to do just that. To do it, first package our two coordinate functions, x of t and y of t, into a single complex valued function, f of t, which outputs x of t plus I y of t for any given t value. Now, observe that we can always express a complex valued function in polar form as r of t times e to the I theta of t, where r of t is just the absolute value of f of t, which is just square root of x of t squared plus y of t squared in this case. And theta of t is the full angle function of the point, which, remember, we're trying to avoid computing directly. If you take a step back, this formula should make sense, right? e to the I theta of t is a complex number on the unit circle that makes the same angle with the positive x-axis as our point. And if we scale it up by r of t, the point's distance from the origin, it will coincide perfectly with our point. Okay, now here comes the trick. Take this polar equation for f of t and divide both sides by r of t to get f of t over r of t equal to e to the I theta of t. Now we'll take the derivative of both sides. One of the really nice things about complex numbers is that many of the algebra and calculus rules you're used to for real numbers and functions work in exactly the same way in the complex setting, and derivatives are no exception. Even though all the functions here are complex valued, the familiar derivative quotient rule applies. So on the left-hand side, we get the usual expression f prime r minus f r prime divided by r squared. But what's really cool is the exponential derivative rule works the same old way as well.